good afternoon, not good morning, until tomorrow. Okay, so let's see here. I did something wild and crazy with our lab last week, but I see two people have checked it out. I actually got Steve, and I know some of you probably know Steve Brown. I got him to join as well, and Joya, who is also in the department, but she teaches other things, so you probably haven't had her. But what I did was, and I'm kind of realizing now, I think the deadline was a little bit ambitious, so I'll extend it so that you'll have reading break to work on it. Let's see here. So first of all, there's this GitHub Classroom link, but it wasn't working. So it was working for me, but not for everyone else. So I don't know what's going on there, but you can try it, and it's just a shortcut, but you can just go to classroom.github.com if you want to log in, and that's totally fine. So for last week, let me see here. I'm gonna screenshot this. Done. Bring it in. I'm just gonna crop this as much as I can, which wasn't very much. Okay. So I'll extend this. I will extend this until oh, awesome. And yeah, really good tutorial, right? To be honest, I didn't work through it. I read through it, but I didn't work through it myself. But I thought it was pretty good. So of course, they're doing amazing work over there at GitHub. So so I know who's in there and who's not. So, but I'll extend this so that you'll have until the end of reading break, which is, I'll extend it until, now I can't remember, the 27th, until February 27th. I think right now it's set to be due on Friday probably, but if I haven't changed it to February 27th, I will. So you'll have reading break to go through it. Okay. And so what we're doing is I'm just getting you set up with GitHub, and trust me, I know when you're first, oh my gosh, you guys don't know when reading break is? It's next week. No classes. I always joke that I wish I wasn't teaching classes all the time so that I could get some work done. And I felt like that as a student, and I feel like it as a teacher. And it's just nice to not have classes for a little bit so that you can feel like, okay, now I can really focus on some stuff and get stuff done. Or I guess, hey, so that means you didn't see my funny here? My plans for, well, it's reading break, but spring break is usually what the Americans call it. You have to click it, but he does move around. Pretty cute. I usually go into it hoping to get a bunch done, and then it's just nice to have a little bit of a break too. So, so reading break is next week, and I hope that you're looking forward to it. Okay, so means no classes next week, right? And so I'll extend this until February 27th. And yeah, so you'll at least have some time to kind of focus on, I know all the projects that you have going on right now. And confession time, it felt a little unfair to make you hand stuff in when I haven't even had time to mark your labs. I know heading into the weekends are like mini spring breaks. I have all these good intentions and I'm gonna get all this done, and then everything just takes longer than I think it will. And so it's on my radar. I'm assuming everyone is doing really well on the labs. They've been very easy so far. So that's why I'm kind of not too worried about it, but I will get to it. I promise. I'm getting there. So we did talk about the exploratory data analysis. This so far has no due date as of yet. Okay, so here, no due date yet. Okay, so that means it's not for a while. I'll at least give you a week's heads up before. Oh, and I'm just reading the chat. So the two assignments, the Python GitHub, only the GitHub one has a due date. Okay, so so that's the one to work on. This setting up, replicating the textbook code in your own document, it's really for you. And so I want you to use that as kind of a library of code. Okay, and so I want you to develop it, and I will get you to hand it in, but I feel like maybe at the towards the end of the term might be a good time. But remember, it is mostly for you, right? I don't care. I can read the textbook. I have this code already, and so it's just for you to have. Okay, and so I will make you hand it in to show off all the work that you've done, right? But let's focus on the GitHub setup. Okay, so what I was starting to say was, before you guys blew my mind that you didn't know when reading break was, so what's really difficult and what's exhausting about going into this field especially is there's so many things that you don't know. Okay, there are so many tools out there that we could be using, that all the cool kids are using, and there's not enough time in a 2-year program to cover all of that. Okay, but one of the things that we should be using is version control, which is Git, or we use it through GitHub. Okay, and so the GitHub assignment, you should be able to just commit at the end. I think it asks you to commit at the end, and then I'll know that it's complete. But I can go in and look at your code. So what's nice about working, or I can look at your progress. What's nice about working in GitHub is you save different versions, and but also I can log in because you're in my classroom, and that's why I'm getting you to sign up for my classroom here. And then I can kind of go in and see where you're at and check to see how things are going. Okay, and so there's this invitation link, and like a lot of the cool things that we're using, it just kind of holds your hand through the whole process. So I didn't do any instructions there because it was very self-explanatory. You click the link, and I got 2 people to try it before I posted it for you guys. And so you're going to click it here, and it's going to walk you through. If you don't have a GitHub account, it'll ask you to make one first, and then you can sign in, and then you can accept my assignment. Okay, and then I'll see you on my roster, and I'll see that you accepted my assignment. And then there's a bunch of instructions there. Okay, and so here, follow the instructions posted in the assignment. And maybe what I'll do is for lab on this Friday, how about we just keep working on the GitHub, right? So maybe take that time or whatever time you want and just here, use this time, or maybe I'll do this. So for this Friday, use this time to start the GitHub assignment. Okay. How about that? So nothing new for the labs this week, but you can use that time to get started on that GitHub assignment. So like I said, one of those core things, if you're reading, and what you should be doing is you should be reading job descriptions for jobs that you want, right? And then just kind of start checking things off that you maybe know or feel like you could easily learn, right? And so, and that's why I'm introducing the Python here, because we know some are, right? And that means we can easily learn some of this Python as well, right? And so the more you know, right, the bigger your library is, the more hireable you are, okay? And so, so there's a lot of things that we could be doing, right? And there's a lot of programs that we don't introduce at all, or I have never heard of, but are probably really cool, right? And so it is overwhelming, right? And so I'm just kind of slowly I'm not so slowly, I'm introducing you to all these things that are kind of the core things that we need to know, right? So GitHub is one of them. Being able to work in GitHub is very, very, very important. I don't think anyone would take you seriously if you're not comfortable working with Git or GitHub, especially. So that's going to be really important. Okay. I'm doing this for you. I do everything for you. You, the collective you. Okay, so today I kind of planned on doing all of this today, which is a lot of no problem. A lot of distributions. And my fear is when I wrote out all my notes, the notes are about twice as long as what I can usually cover in a class. So I suspect that we're going to have to continue on Thursday. But we're just going to talk about all these distributions. And like I've been saying, just continue reading through the textbook. So we're in chapter 2 right now, and I want to do test 1 after chapter 3. So I want to do test number 1 after chapter 3. Okay. Chapter 3, it's going to take us a little bit to get through chapter 3. So we're still a ways out. It's going to be quite a bit after reading break, maybe a week or 2. So just be aware. And once I see how today goes, how quickly I can move through these distributions, we'll know better. Okay, but that's my goal, is after chapter 3. So for test 1, I know it's been a while since we started, but remember, we didn't pick up the textbook until kind of a couple weeks in. So that's why, and we spent a lot of time on review, and that review is going to come into play in chapter 3 as well, and 4. So it's all coming together. But okay, so that's my goal. All right. So as a little bit of review, traditionally, so in traditional statistics, which is how we approach stat 230. So we use very traditional approaches, and that's what most fields are still using, right? And so data science is kind of this, they're kind of saying, oh, well, we don't actually need that stuff anymore because we can approximate things just using the bootstrap, right? But traditionally, we've relied on sampling distributions, right, to figure out the variability in a sample estimate. Okay, and so traditionally, we have relied on sampling distributions things like, so such as X bar follows a normal distribution with a mean mu and a standard error of sigma over root n, right? That's a sampling distribution of X bar, right? So if I look at X bar, where can I expect it to have come from, right? And so, and traditionally we would say, well, I'm going to assume it came from a normal distribution with this amount of spread, right? Sigma over root n. I don't know sigma, I know n, but I don't know sigma because that's from the population. And so what can I do? I can estimate the standard error by using s over root n, right, from the sample. Okay. So we use these sampling distributions to estimate the variability, which is the standard error. Okay, but because we're doing an estimate, right, then the variability of a sample statistic using s over root n, for example, right? Because I'm trying to estimate sigma over root n. So what's my best option? Well, it would be to use s over root n, right? And we spent a fair amount of time in stat 230 developing this idea of, okay, we've got the sampling distribution, and now if I use s instead of sigma, then I'm going to be using a t distribution, right? And so it's not, it's normal, but with some degrees of freedom. So the shape changes depending on the degrees of freedom. And so, so that's the traditional approach, right? That's how we've been doing things for a very long time, right? And so, but now, with computers and kind of computing power, what we can do is we can leverage the bootstrap instead, right? So we can kind of move away from relying on these predetermined distributions and say, no, X bar always comes from this distribution, and this is how I estimate the variability. It's surprisingly accurate, but we don't need it anymore because we can use the bootstrap. And we introduced the bootstrap last day, where we have collected a sample, a random sample. And then what I do is I randomly select more samples from that sample, right? So I'm replacing each observation, I record it, and then I record the mean, and then I develop this distribution of means, for example, if that's what I'm interested in. Then I can look at the center and the spread of that distribution of the means, and that's how I'm going to be able to estimate the variability now, right? So let's write some of that down. So however, with computing power, we can use the bootstrap the bootstrap to estimate the variability of any sample statistic, right? Even the ones that we didn't know the distribution of before, that no one had developed the distribution for. And of course, tons of work went into developing these sampling distributions. So we're not going to ignore it completely, because someone did put a lot of work into it at some point. But now with the bootstrap, we can kind of move away from that and not rely on it so much. Okay, so the variability of any sample statistic. Okay. A sample statistic, or a statistic, is just a measurement from the sample, right? And so one of those things would be the mean, X bar, right? Or potentially the standard deviation, S, or what about, there's all kinds of things that we can measure. There's a measure of skew, there's a measure of kurtosis, there's a measure of, for pretty much everything. So we can use the bootstrap to look at that distribution. Okay. And so what we saw was, we don't just use the bootstrap to look at the variability. As soon as we have some distribution that we see, right, that we've developed using the bootstrap, I can also make it a confidence interval, right? I can cut off the outside points, and then I have a confidence interval for the true mean, for example, or the true standard deviation, right? And so we can also use the bootstrap to, and maybe what I'll do is I'm going to bump this up so it stays, because it's all coming to the end of the review here. We can also use the bootstrap to construct confidence intervals. For any sample statistic. Okay, so that's kind of the end of our review here. I think I've got a page break right there, so I don't want it to look too weird once I save it. But so now what we're going to do today is just introduce some of the other distributions that come into play. Okay, let's keep in mind that there are many other distributions that we could talk about, but these are the ones that we're going to focus on for data science, and it'll be quite obvious why that is, right? And so right, some of the key things that we would be interested in from a business perspective typically involve things like success failure, right? Maybe that rings a bell from the binomial distribution, right? What about the time to failure? How long is it going to take until this machine breaks, right? We can use the exponential distribution, or what we call the Weibull distribution, right? And so a key part of us being data scientists is knowing when to use what distribution, what's appropriate, how can I model this behavior, what distribution do I need in order to model what I want, okay, what I'm actually interested in, right? And that's very difficult, but today we're just introducing the different types of distributions. So we're not going to use them. The textbook shows us how to simulate them, okay, but and how we could, you know, pretend to have an exponential distribution, for example, right? And so but that's as far as we're going to go in this chapter. And then when we move into hypothesis testing, then we're going to show how do we use these distributions to test the hypothesis, right? Okay, so we start with a normal distribution, and I don't want to knock the normal distribution too much, but I do kind of agree with what the textbook is saying, that, okay, well, it's kind of outdated. We don't really need it. Nothing is truly normal. There's even a fun example in the textbook where, where they generate randomly selected normal data. So they have a normal distribution and they pull from that normal distribution. And even when we graph that, it still doesn't look perfectly normal. And so there are very few things that are actually truly normal, right? And so, but that doesn't matter. It's still what we use because it is a good estimate for most things. It's a decent estimate for most things. And so we'll start with the normal distribution. And I'm only putting them this close because I've got a page break here in case it looks weird right now. So if we start with the most common distribution that we have, it is the normal distribution, and that's mostly historical. So the most common sampling distribution is the normal distribution. Is the normal distribution. Okay. Now, let's remember that very few things are truly normal. Okay, so here, let's also make a note that very few things are truly normal. Very few things are truly normally distributed, is what I mean, are truly normally distributed. But, right, it's still valuable. Why? Well, knowing that something is normally distributed opens up this kind of tool that we can use. We can approximate probabilities, right, using the normal distribution or the Z curve. But now let's just be grown-ups and use the empirical rule. You might remember the empirical rule is the 68, 95, 99.7, right? And so if something is roughly 95%, that's interesting. And I don't really care if it's 97% or 98%, right? If it's somewhere between 95 and 99.7, that's good enough, right? And so now we have these approximations that we're going to use instead, right? So we're not going to use the Z table because we do that in Stat 230, right? To try to find areas under the curve. We do that and we work hard at that. But the goal is to find probabilities. And now we're going to use software to find those probabilities, those exact probabilities, if we're interested. Often we're not truly that interested. We just want to know a ballpark, right? And so what we're going to move towards is just to get an approximation, we're going to use the empirical rule. Okay. So knowing we have a normal distribution, so knowing we have a normal sampling distribution, allows us to approximate probabilities. Allows us to approximate probabilities using the empirical rule. Which is what? The 68, 95, 99.7 rule. But again, we're growing up, right? So we should probably call it the empirical rule, which is what it's actually called. right? We call it the 68, 95, 99.7 rule to kind of help us remember what's going on, right? But remember, anything within one standard deviation, roughly 68% of the curve is within one standard deviation, 2 standard deviations, roughly 95. Some people stop after that, right? And then 3 would be 99.7, but often all we need is it in the 0 to 68 range, or is it in the 68 to 95 range, or is it beyond 95? So you can see how those would be good enough. Yeah? And so remember, if we have a normal distribution here, then from the mean, I can move out mu minus sigma and mu plus sigma. And this area is 68%. I can move to mu minus 2 sigma and mu plus 2 sigma. I guess I should move it a little bit closer in there. 95%. And then we could go to 3, but at this point, right, if a probability is higher than 95%, right, we kind of stop caring. Okay. So it does go to mu plus 3 sigma and mu minus 3 sigma. There's a business, I think it's like a certificate program, the 6 Sigma program. And I'm pretty sure it's supposed to help your business become more efficient or something, but I don't know. I obviously haven't looked into it too much. But I suspect that it's talking about these 3 standard deviations. I made a messy one, but we did it properly in Stat 230. So, right, so here 99.7%. So you remember this, hopefully. And of course, there's 0.3% in the tails remaining, and they go to infinity and positive and negative infinity, but we're gonna not talk about that so much. Okay? So we can use the empirical rule to approximate probabilities, right? This gives us ballpark figures. Okay, is it less than 68% or roughly 70% if you want to get sloppy, right? Or is it more than 95%, that kind of thing, right? And so what do we need? Well, in order to use this approximation, we need to know how many standard deviations an observation is from the mean. So to use this, we need to know how many standard deviations which is sigma, an observation, which is x, is from the mean. Yeah. So this is where the z-score comes from, right? Because now I can standardize using a z-score. And remember, z is x minus mu over sigma, right? And so that is the z-score. Okay, the z-score is how many standard deviations an observation x is from the mean. So this is called standardizing X, or normalizing if you prefer, or a z-score, all those things are synonymous, right? They mean the same thing. So one thing that we need is we need to be able to check to see if a distribution is normal, or if we can just kind of call it normal at least. So one thing that we can use is the QQ plot, which we've seen before. And so we can visually assess a normal distribution by using a QQ plot. Okay. What does a QQ plot do? It takes the mean, and it's no longer mu, it's going to be the sample mean and the sample standard deviation. And what it's going to do is it's going to plot the perfect normal distribution. So what would those values be? What would those standardized values be if we followed a perfectly normal distribution? So what we're going to have here is the normal distribution values with the same mean and standard deviation. Okay. So it's going to plot those theoretical values. Okay. So it looks at the mean and it looks at the standard deviation, and it says, okay, with that mean and that standard deviation, I expect a point that's this much on the normal distribution scale or on the Z scale. I expect it to be this much in reality. Now, if X and Y are the same, then what happens? Then I have a line across the diagonal, right? Sorry, cut out here. There. And so here on the y-axis, we're going to have the z-scores, which is the actual data. So here we have our observed values. Okay. And so points, and maybe I'll use a different color here. Observed values that fall on this line, right, are exactly the same as the theoretical values, right? And so they would be considered normal. Observed values, and maybe I need one more line here. Observed values that fall on this line are the same as the theoretical line, or theoretical values are the same as the theoretical values, therefore normal. Right? So if the points are on this line, then we have a normal distribution. One thing that I want you to remember is that we allow deviations in the tails, right? Because we're never going to have a perfectly normal distribution, but as long as a good solid stretch of this, of the points are on this diagonal line, then we can say we have a normal distribution. Okay, and so we allow some deviation in the tails. We allow some deviation in the tails. right? Like I said, even that one where we pretend to pull values from a perfectly normal distribution, and then we make a QQ plot, even those values have some deviation in the tails. So we can't expect things to fall exactly on the tails or all the way on the line, but for most of the line, we're expecting it to fall on the line if it's normal. Yeah. So that's a recap on, how do we know if it's normal and what can we use the normal distribution for? But let's move on to kind of more interesting things that we haven't spent so much time on. And so an easy segue would be to long tail distributions. So long tail distributions let me see. Yeah. I'm just briefly going to talk about long tail distributions because there's not a lot going on here. It's more of an idea that, okay, even data from a normal distribution deviates from the normal distribution in the tails, right? And so that's where we get this long tail distribution idea from. Okay? And so especially if we're looking at raw data, then we're going to have some deviation in the tails. Okay. And so the normal distribution rarely applies to raw data. And we often see these long tail distributions, especially in raw data. Right? We often see long-tailed distributions. Right? What does that mean? Right? And maybe I should clarify before I ask that. We often see long-tailed distributions instead of perfectly normal distributions, right? Instead of perfectly normal distributions. So what does that mean? And maybe I'll use a different color. So if I have this perfectly normal distribution, and I'm going to try my best to draw it, but it's not going to be that good, right? Then maybe I have something that looks like this. That would be a perfectly normal distribution. So now, if I think about the term long-tail distributions, right? So not necessarily a skew. So it's going to have that same shape. But if we think about a long tail distribution, the tails go in either direction, right? So usually a skewed distribution has a long tail in one direction, right? And that's good, right? And we'll talk about skewed distributions. But if we have a long tail distribution, that might look like this. I'm trying to remember if it bumps up. Something like that. Okay. So what does that mean in terms of these extreme values, right? Especially if we focus down here, right? Remembering that the area under the curve is the probability. Recall the area under the curve is the probability. So then what we're going to see if we focus up here where I drew it really, really kind of extreme and obvious, for these long tail distributions, there's more area under the curve, right? And so, and I feel like I should have flattened this out. Sorry. I need to draw that again. The tails are going to look the same. Well, sort of. There. That's better. Yeah, so that's one of the things, right? The probability is never zero because there's always some area under the curve, right? And so, but if we focus on this, let me see here. Now you guys are just showing off all the things that you know, all the things you know, and I'm so proud of you. So that's good. So here, what happens if I've made more area in the tail? Well, that means I'm allowing for a higher probability of these extreme values happening, right? And so if the area under the long tail distribution, right? So this means that there's a higher probability of extreme values in the long tail distributions. In the long-tailed distribution. So, but maybe I'll just use the singular. Right, so I actually have kind of more area under the curve, which translates to a higher probability, right? And so, so what does that mean? If I'm assuming that things follow a normal distribution, then I would say that a value out here, for example, would be very, very unlikely, right? But if it's actually following the green line, right, then it's more likely, right? The probability is higher than what I thought it was initially, right? So you can see that kind of problem, and you know how we solve it. We solve it by using the t-distribution, which changes the shape depending on the sample size typically, but it can be other things too. Okay, so we have solutions. We have these traditional solutions that we've worked through and worked very hard at developing. We didn't develop them, but someone did, or a team did probably. And so what we're saying is that extreme values and maybe I should start by saying in long-tailed distributions, extreme values are more likely than expected by the normal distribution. So in long-tailed distributions, extreme values are more likely than expected by the normal distribution. Okay, so that's something to keep in mind, right? We've got these extreme values, but is it truly extreme? Because if I have a long tail distribution, then maybe it's not as extreme as I initially thought it was when I standardized things, right? So we do use that cutoff of, you know, Z, if it's greater than 2, then I suspect that it's going to make me reject the null hypothesis. Whoa, 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 whoa. Where's this coming from? Well, you guys know it already, right? And so If a z-score is larger than 2, then that's a good cutoff, right? But now if we have these long tail distributions, we can have slightly larger numbers, as we saw with the t-distribution, which is our next distribution. Okay, so you might have heard it called the student's t-distribution. And I don't know if you know the story of the t-distribution, how it was developed, but I think it's William Gossett. I think his name's William, but Gossett, anyways, was a statistician, and he worked at Guinness Brewery in 1908. I only remember that because I wrote it down. And he studied the distribution of the mean, and so he's working at a brewery, and so he's collecting samples all the time, and he's analyzing the mean. And in 1908, he was definitely not using a computer. So he had to find a way to represent the distribution of the mean without constantly mapping it and doing all these calculations. And so the reason for calling it the student's t-distribution is because he submitted a paper, and trying to remember, I think it was Biometrica, which is a journal. And Guinness, who he worked for, said, no, you can't use your name because then our competitors are going to know what we're up to, and we don't want that. So he submitted it under the name student, but now we know the whole story now. So, but that's why it's called the student's t-distribution. And it's just kind of a cute backstory. But what is it? It's a distribution that's very similar to the normal distribution, except it allows for thicker tails, right? These long tail distributions. Okay, and so the t-distribution, the t-distribution is shaped like the normal distribution, is shaped similar to the normal distribution, I'll say. But has thicker and longer tails. But has thicker and longer tails. So what I want you to start thinking about is, okay, well, when I say it has thicker and longer tails, I want you to think, okay, that means that I'm allowing for more probability for those extreme values. Okay. So this increases the probability of extreme values compared to the normal distribution. Oops. Okay. So that's a good thing, right? Because that's what we just said. Very few things actually follow a normal distribution. So we need more area in the tails. Now, what we're going to find is that the shape of the t-distribution changes depending on the sample size. And of course, if we increase the sample size, eventually we're going to have a sample size the size of the population. And that's when we hit the normal distribution. Right, so the t-distribution tends towards the normal distribution or the z distribution if we increase our sample size to be large enough. Right, eventually we're going to hit the population, and then we're the same, right? But most of the time we're not going to be looking at the population size, and so then we use the t-distribution instead. Okay. And so the t-distribution oh yeah, so it's one of these long tail distributions and the most common one that we're going to use, right? And so good call. Yeah, I do want to link those up because here I said just in general, we could have these long tail distributions. And then one of the most common ones that we actually use is the t-distribution. Good. So the t-distribution changes shape, not really the shape, but more like the thickness of the tails, right? So mostly, so I'll just say in the tails. So the t-distribution changes shape. So remember, right, if we have a small sample size, then we make lots of room in the tails. And then as we increase our sample size, we tend towards a normal distribution, right? So the t-distribution changes shape, mostly in the tails, but of course the center kind of changes as well. Okay. Depending on the sample size. Depending on the sample size. Okay. This is communicated by the degrees of freedom. What we're going to find is that a lot of these distributions have degrees of freedom. How you find them is going to change depending on the distribution. But in general, this idea of degrees of freedom dictating the shape is not, it's not going to be unique to the t-distribution. It's going to be for most distributions. So the t-distribution changes shape of the tails depending on the sample size. So we communicate this by the degrees of freedom, which, for example, could be n-1 in the most simple case, but there are many times where we can use the t-distribution and learn a lot about a sample statistic. Not just one sample mean. We've seen it for 2 sample means. We've seen it for matched pairs. We can use it for testing the correlation. We can use it for testing the slope. There's all kinds of things that we can use the t-distribution for. So it's often included in output. So so we need to know how to read it and understand it. Right, but in terms of approximating the variability, we're going to use the bootstrap instead. Okay, so t statistics are often included in statistical output so we need to know how to read it, right? So we need to understand it and kind of have a good understanding of it. I said that twice as important. So we need to, let's see here. We need to understand it, but data scientists will often just use the bootstrap, right? And to learn about the variability, right? Or the sampling error. So, but data scientists will often rely on the bootstrap to answer questions about sampling error. To answer questions about sampling error. Okay. Good. So we've been talking about numerical data so far, right? And so what if we talk about some categorical data, specifically binomial data? Then we have the binomial distribution. Is an option. What are some of the criteria for having a binomial distribution? And I know we've worked with the binomial distribution formula to find probabilities. And so let's remember some of the things that we have to have in order to classify it as a binomial distribution. We have to have two possible outcomes, two and only two, just to clarify, possible outcomes. Right, so kind of a yes, no, success, failure situation, etc. Okay. And those two possible outcomes have to have some fixed probability, right? So the probability has to stay the same for every trial you do. Okay, and so what does that mean? It means that those probabilities are independent of each other, right? And so the outcomes, have fixed probabilities. Okay. So usually we're going to recap the yes, no, success, failure as 0, 1, right? Outcomes. Maybe I'll bump that over here. 0, 1 outcomes. What's really important is that the thing that you're interested in is what we code as a 1. Okay, and so the 1, right, where 1 is used for rare outcomes, which are going to be the ones that we're interested in. So where 1 is used to denote the outcome of interest, and usually it can be a rare outcome. Okay, so often a rare outcome, right? So things like, let's say the airbag not deploying in a car, right? Most of the time we're not in a crash, and most of the time, even if we're in a crash, the airbags deploy. But my job, right, and the job that maybe a car manufacturer would be interested in is, okay, well, how can we prevent those rare instances where the airbag does not deploy? Those are the ones that I'm interested in. How can I figure out what's happening to make that airbag not deploy, and then I can fix it, right? We need to figure out a way to model that. So usually the 1 is the thing that we're interested in, right? And so, and then everything else can be coded as a 0 because those are outcomes that you don't care about, right? So many scenarios we can boil down to a 0, 1 situation, right? And so just remembering that the 1 is the thing that we're interested in. Okay. And so the binomial does what? It gives us the probability of exactly some number of successes, k successes, okay? And so, or maybe x successes if you want to match the textbook, but we used k, but you can use r or x or whatever. Okay, so the binomial distribution is the frequency distribution right? How often do some things happen? If we know the probability, then and how many trials we've done it in, right? So it's a frequency distribution, and that's what lets us calculate the probability, right? Of the number of successes, which we're going to denote by x, in a given number of trials. So in a given number of trials, I'm going to use the pound symbol here. In a given number of trials, n, with the specified probability of p, with a specified probability of success which is p. Okay. And maybe I should say probability of success in each trial. Okay. Remember that probability has to be fixed. Okay. And of course, we're not going to do this by hand anymore. The textbook walks you through how to do the binomial calculation in R. And of course, it's really easy. What does it need to know? It needs to know how many successes you're interested in, and it needs to know how many trials are you doing, and it needs to know the probability of success. And then it can just kind of go from there, right? And so one thing that you're going to find is that you're going to be facing problems like, what's the probability of exactly 4 successes in 20 trials, right? If the probability is 0.2, for example, just using the example I had from last class, so or my previous section. And so if I try to do something 20 times, what's the probability of exactly 4 successes? If the probability of success is 0.2, we can find that, right? And R just uses the same formula that we would. And I'm not going to write it. Well, remember, recall the probability that x equals, let's use the lowercase x, is n choose x p to the x times q to the n minus x, right? We're not going to use that. I'm going to say use R to calculate now. We use R to calculate now. Okay. But one thing that we didn't introduce was this idea of, okay, well, what if I want to know the probability of no more than 4 successes in 20 trials? What am I looking at? Then I'm looking at 0 successes, or 1 success, or 2 successes, or 3 successes, or 4 successes. So I'd have to add all those 5 probabilities. So I'd have to find them all individually, and then I'd have to add them all up, right? That's a lot of work. And of course, R can just do that for us. So what we need to learn about is the difference between a PMF and a CDF. Sometimes the PMF is called the PDF, which I'll call it sometimes. And so the difference is that the PMF is the probability of exactly X successes, right? Whereas the CDF is the cumulative distribution function, so up to and including that many successes. Okay, and so the reason I bring that up is because the Python code does rely on the PMF versus the CDF. So that's why I introduce it here. And so we can find the exact probability, or rather the probability of exactly X successes. And this is what we call the PMF. The PMF, and maybe I'll say, or PDF, which is the probability mass / distribution function, depending on which one you prefer. They kind of mean the same thing, so it doesn't truly matter, but so the probability of exactly X successes is called the PMF. Okay. Whereas the probability of less than and including X successes, and of course, remembering that the total probability has to be 1, then if I know the probability of less than X successes and including X, then I can find the probability of more than X successes, right? And so we can still use that to move back and forth. So the probability of less than and including X successes is called the CDF, which is the cumulative distribution function. Okay, so just to highlight the PMF versus the PDF, right? So some example, or an example here is if I want to know the probability that X equals X versus the probability that X is less than or including X, then we would use different code, right, to do that. Okay. Okay. Good. What's interesting is that as we increase the trials, right, the number of trials, the binomial distribution tends towards the normal distribution. And that is totally mind-boggling. I don't know if I wrap my head around it still. I've accepted it, but it's one of those things that it's like, what? That is so weird, right? But those probabilities start to follow a normal distribution. So, or rather the frequency distribution tends to a normal distribution. So let's jot that down. And I've got a page break, so that's why I'm writing it so close. As we increase the number of trials, we will find the binomial distribution tends towards the normal distribution. Oh, whoops, I skipped some words there. We will find the binomial distribution tends towards the normal distribution. Well, this is especially true if the probability of success is close to 0.5. Okay, so this is especially true when P is close to 0.5, right? If you have a really, really, really low probability of success, then that's hard to pick up, right? And so then you would have to look at so many trials before it started looking relatively normal. And so, and we can check that, right? We have to assume that we have at least 10 successes and at least 10 failures. So n times p has to be more than 10, right? So recall n times p has to be greater than or equal to 10, and n times q has to be greater than or equal to 10, right? I have to expect at least 10 successes and 10 failures in order to use the binomial, the normal approximation to the binomial, right? We're going to parking lot that. Don't worry too much about that. That's just something to keep in mind. But let's just remember that the binomial tends towards the normal distribution. And why is that especially true when p is close to 0.5? Well, because if I have a really small value of p here, such as 0.01, right, then my n has to be really large in order to get it to be greater than 10, right? So that's why that's true. And so we can find the mean and standard deviation of the binomial, or sorry, we're going to use the variance and variance because we're adults now, right? I still like the standard deviation. Why? Because the units are the same as the data, right? For the variance, the units are going to be squared, and that can make things complicated a little bit, right? But remember, the variance and the square root is just this, or sorry, the standard deviation is just the square root of the variance. I was saying the words, but not properly. So we can find the mean and variance of the binomial distribution. We say that mu is n times p, which our brains are really good at doing, right? If I say I tried something 20 times and the probability of success is 0.2, then how many successes am I expecting here? I'm expecting 20 times 0.2, right? Which is exactly what it's doing. And the mean is the expected value. The expected value of x, which is the number of successes, right? X is the number of successes. And the variance is NPQ, right? Where, of course, where Q is 1 minus P, the probability of failure. Okay. I think I'm all out of time, but I think that's a great place to stop. So just as I suspected, we'll keep going through distributions next day, but that's totally fine. If you have any questions, let me know. Otherwise, I will see you on Thursday. Stop this recording.